Thank you. So, hi everyone, and in this presentation I'm going to talk you about a very high-level overview of the work that we have been doing about floating point round of error analysis of avionics software. So, everyone knows that writing floating point or in general final precision numbers code is challenging. So, in the context of floating point numbers, we have, of course, the runtime exceptions such as not a number or division by zero. However, we also have a kind of a subtle errors, which are round-off errors. In this case, we still obtain a result. However, this result can be very different from the one that we will have obtained using exact real arithmetics. And this is even worse in the case of the so-called unstable guards. So imagine that you have a if-then-else or a loop guard, and inside the evaluation of the arithmetic expression in your guard, you have a a round-off error that makes the Boolean guard have a different value with respect to ideal real number evaluation. Well, this can lead to divergence in the control flow of the program. So the divergence of the results is even bigger. So we have found several examples of misbehavior of floating point or in general final precision implementation of several libraries for avionics software developed at NASA or not. And this ranges from geofencing application to detect and avoid systems. However, in this presentation, I'm going to concentrate in this particular example, which is the ADS-B compat position reporting algorithm. So to give you a background on this, is ADS-B, so automatic dependent surveillance broadcast, is a technology that will support the next generation of avionics software and of traffic management systems, and it will augment and eventually will replace radar. So the idea behind ADS-B is that the aircraft will automatically and periodically broadcast a message that contains some information about, for example, its position and its velocity. And it's going to broadcast it to the nearby aircraft and to the ground station. And this is mandatory since the beginning of 2020 in the USA and in Europe. And ADS-B, thousands of aircraft are already equipped with ADS-B, and it's actually used all around the world already. So CPR is a key component of ADS-B, and is the algorithm that encode and decode the position of an aircraft. The problem is that in the ADS-B message, we just have 35 bits for both the latitude and longitude together. And this is equivalent to have 17 bits for each dimension. And this means that we have a 300-meter granularity, which is, of course, not enough. No, and you should tell. You should have the MIT guys that did this algorithm. Well, that's the list of your problem in CPR, you will see. So this is not precise enough. So the idea behind CPR is to divide the globe in some zone. So you have two different kinds of encoding, an odd encoding and an even encoding. And depending on this, you will divide the globe in 59 or 60 equally sized zones. And then you will divide each zone into the 17 bins. Then, with the zone number plus the bin number, you can imagine this as a small square of 5 meters per 5. And this will correspond to the position of the aircraft. So, the CPR encoding, it's actually very easy. It's this. This expression right here that computes the bin number. So the interesting thing about CPR is that just the bin number is broadcasted. So you have 17 bits, so you have 17 bits for the latitude, 17 bits for the longitude, and 1 bit that said that if your encoding was an odd or an even encoding. And you will see, you just have the bin number, you don't know in which zone it is. So yeah, that's not very useful. Well, the CPR decoding, it will actually need 2 messages to recover the position. And for doing this, he will use 2 messages, one even and one odd, so 2 different decoding that needs to be sent sufficiently close to each other. And then with some computation that uses the zone offset, he will determine the correct zone and then the correct position of the aircraft. What's the problem? Well, pilots and manufacturers have reported errors in using the CPR algorithm. For example, this situation was reported by Air Services Australia in 2007. So the aircraft was here, but CPR said it was here. Well, so during a meeting, some guys from the Federal Aviation Administration asked our group to look into this problem. And what was the problem? Well, the first thing we noticed is that some requirements of CPR were not enough to guarantee the correct operation of the algorithm. So that sufficiently close that they defined wasn't enough, and other things. So what we did was to propose a slightly tightened set of requirements. And then we formally proved in the theorem prover PVS that assuming exact real arithmetic, the CPR algorithm was in fact correct. So the original position, the difference between the original and the recovered position was at most 5 meters. However, when we implemented this algorithm using finer precision, well, we had a huge accumulated round of error. And this is because CPR make a heavy use of the modulus and floor function, which are intrinsically unstable. For instance, we had a test case that using single precision, the CPR algorithm was off by 1,500 nautical miles. And then we also find other test cases with double precision and also fixed point arithmetic. So our solution was, okay, we tried to take the CPR algorithm and try to propose a more numerically stable version that we call CPR star. And what we did was like some mathematical manipulation that will decrease the numerical round of error. And then we used a suite of existing formal methods to prove this new version correct. So what we used was a toolchain composed by PVS, the interactive theorem prover. We use GAPPA, which is a framework for the analysis of floating point program, and we use PRAMA-C, which is a well-known static analyzer for C. So the input of our verification was a C implementation of CPR, the simplified version of CPR, and this was given to PRAMA-C. So PRAMA-C, what it does is computing a wicked precondition analysis, and it will generate a set of verification conditions. And some were given to GAPPA for the one that were related to the floating point or numerical part of it, and some were given to PVS. And we discharged them. And another thing that we did is that we had to prove that this simplified version that we proposed was actually equivalent to the original CPR that included in the standard. And we did it by hand with PVS, like proving with interactive theorem prover. So the result of this was that our CPR formally verified implementation, we have two actually, one with double precision floating point and one with 32 bits unsigned integers. Now it has been accepted to be a reference implementation in the ADS-B standard document. However, in our verification effort, one thing that we didn't like is that it was not completely automatic. Of course, a lot of human intervention was used. The first is that GAPPA needs hints for verify the tight rounding errors, so expertise on how rounding error actually propagate inside the formulas was needed. And also we did a lot of interactive theorem proving by hand, and it was tedious. So this work inspired us to try to automatize all this verification effort. And ideally, what we really wanted to do was having a real number specification of an algorithm, then generating automatically and verifying automatically a C finer precision implementation. So this led us to propose our static analysis framework for floating point program called Precisa. So Precisa does two things, basically. It computes sound and precise round of error estimation with an associated certificate in PVS that can be externally checked in PVS. And also it can generate a C implementation from a PVS real number specification, which is, first of all, it's annotated with pre and post condition on how the round of error accumulates. And the second thing is that instrumented to detect when the control flow diverges. So remember at the beginning of the presentation I told you that when rounding error affects the evaluation of the guards, that may be a problem. So what we did was making an instrumentation of the program to detect these cases, and in this case you get a warning. And then what we did was integrating Precisa with PVS and PromaC, similarly as before. So this is how our integrated toolchain works. So the input is the PVS real specification that is given to Precisa, and Precisa computes two things. One is the rounding error and the PVS certificate that ensures that these rounding errors are correct. And the second one is the instrumented C implementation of this. Then we use PromaC. So this is given automatically to PromaC that computes as before wicked precondition analysis and generate verification condition in the language of PVS. And finally, we check in PVS that this and this are correct. And for doing so, we have developed some automatic strategies or tactics, if you're familiar with COC. So, yeah. So the important thing about this is that no expertise on theorem proving or plotting point is required, so it's automatic. So let me conclude by saying that, yeah, during these years, what we did was successfully integrating different formal methods too. So we have, static analysis based on absolute interpretation, then we have theorem proving, we have pre-post condition analysis, and we integrated this for solving problems. And we have applied this to prove the CPR algorithm and also to prove other avionics software so fragment of NASA libraries such as Polycarp, which is for geofencing, and Titolo, that's for detect and avoid. And of course, there's a lot of future work that we want to do. We want to extend the support we have now for including more data structure. And also we have limited support for loops and recursion. So we want our tool to be applied to a wider range of programs. That's it. Thank you. And these are some references.
Any question?
Have you tried tools like Fluctuate?
Yes.
And it doesn't work?
No, the problem with Fluctuate is, we tried, and we also collaborate with the guys from CEA for a while with this. In fact, the first paper on CPR was with them. But we had to use GAPPA because it generates certificates. And also Fluctuate, we tried to use this, and besides not generating certificate that we really wanted, it didn't work well with the floor and the modulus. So GAPPA was much better with those because you can provide the hints that you provide were more effective. So, yeah.
And the correctness depends on the machine.
Yeah, of course. But we are assuming IEEE.
So do you take that into account, like the division on 80 bits or 64 bits or things like that do not produce the same result on different machines?
No, well, for doing this, we assume the conformance with IEEE standard. And yeah, for the CPR, it was a little bit different because we did it for double precision, that had the problem, and 32-bit integer, so we don't have any others. And for the rest, yes, you're right. In fact, we don't have all the, toolchain until the machine code that will be desirable.
Okay, so you have some semantics of C, which is independent of the machine.
Not of C. We have more like a generic semantics that, we have a static analysis works like this. So we have some semantics that compute like a symbolic, very big expression that is the rounding error. Okay, and this is for PVS actually now. So the part about C is that we integrate it, is that we generate C code. And then this C code, we give it to PromaC, and we use PromaC for that part. Okay. So,
Okay, any other question? No. Thank you again, Laura.
Thank you.
Thank you.